Good afternoon, everyone. Thank you for taking time to join us. Judging from the overwhelming response to this seminar, Best Practices Steam System Startup, this appears to be a very timely topic given the recent COVID-19 situation. You've no doubt heard some major plant startup issues around the globe that have had some tragic results. Our goal today is to share some best practices within the steam system utility for a startup that makes your facility safe and efficient. My name is Cam Spence. I'm the Director of Educational Development for Armstrong International, and I have the pleasure of introducing two senior members of our Utilities System Engineering team. We'll start ladies first. We have Nevena Ardanova. Nevena has 35 years of energy engineering experience in a variety of industrial and institutional facilities. She's a specialist in evaluating, auditing, design, and system optimization of new and existing energy systems. She holds a BS degree in mechanical engineering from Sofia Technical University in Bulgaria. Nevena is also a certified energy manager by the Association of Energy Engineers since 1997. She's DOE qualified for the best practices steam system specially, and recognized and awarded a certificate of appreciation by the U.S. Department of Energy. She's also part of a project team for the ASME-EA, which is part of the Energy Assessment Standards for Steam System. She's an active member of the Association of Energy Engineers, part of ASHRAE, a member of ASHRAE, and also as part of the Society of Women Engineers. Nevena is a senior utility system engineer with Armstrong. So today she's riding shotgun with Prathamesh Tenekar. Prathamesh has more than 15 years of experience in the energy sector. He holds a master's degree in energy studies and is an EVO certified measurement and verification professional with a passion, and I would say a natural big passion, for the hands-on approach for a cleaner energy generation and conservation. He has exposure to global energy scenarios, has worked on projects all over the world. They would include regions such as the US, Brazil, Philippines, Malaysia, Vietnam, Singapore, India, and Sri Lanka, implementing the energy conservation measures that they've found. So from there, I'm going to turn it over to Prathamesh to take it away.
Thank you, Cam, for that wonderful introduction. Hello, everyone. A very warm welcome to today's webinar. Over the next 25 minutes, today we'll be going through some of the best practices for getting your steam system up and running in a safe and reliable manner. This webinar brings to you an extremely distilled and condensed version of a very vast topic. The intention is to give you a broad idea of what can go wrong and how to avoid the most common pitfalls. During the webinar, if you feel there is a topic that needs to be addressed in detail, or if you feel we should have a custom webinar suited to your organization for your employees and colleagues, please let us know and we'll make it happen. As you may have realized, to optimize bandwidth, participant mute function is enabled, meaning you can hear me but I cannot hear you. To make this webinar lively and get your thoughts and ideas and queries, we'll be running a live Q&A during webinar. To help with this, Q&A tab is available on the right hand side of your screen. If you have any questions, just pop them in there. And if you miss anything during the webinar, don't worry. We'll very shortly send you a link of this recording to your email address. While discussing the best practices, it is important to briefly pause and dwell upon the current global business environment. Many industries and institutions like universities and hotels are starting their utility generators after a prolonged shutdown. This is very unusual, and so it calls for a more careful approach. Though globally, manufacturing and hospitality industry was largely expecting a shutdown, there was, and still is, a lot of uncertainty about it. Many industries, despite best of planning, found themselves scrambling for time and resources to follow the normal shutdown standard operating procedures or SOPs. In context of COVID, industry can very broadly be classified into two groups. One segment or group that had to shut down its operation completely, and the other group which changed its production or product mix to either make changes to conventional products or simply moved on to manufacture altogether different products. Several manufacturers converted their production lines to produce hand sanitizers, ventilator components, and other personal protection equipment. The utility requirement for manufacturing these products is obviously very different from what these facilities are designed for. However, as we speak today, many of these manufacturers are getting back to manufacturing conventional products. Also, now that the restrictions are slowly eased out in some geographies, there is a sudden resurgence of pent-up demand. Institutions and industrial units are running against time for making available the much needed utility services. While some businesses have employees working from home without affecting productivity, manufacturing and institutional sector for sure is not one of them. To comply with health guidelines while running production lines, businesses are taking measures such as physical distancing, limited employees on production floors. This comes at a time when industry is already struggling to keep up with aging infrastructure and retiring workforce. We have already started to see the impact of all this. Over the past couple of weeks, many unfortunate startup related accidents are reported. These accidents could have been avoided by paying attention to details and simply following basic engineering practices. Let's start with the heart of system, the boiler. Boiler, as we know, is a pressurized fire vessel, meaning there are multiple complex physical and chemical interactions happening within that closed confined space. To put it simply, boiler startup should be done only by a qualified technician. Every boiler type, make, and usage history is unique and must be respected while attempting a startup. In 2007, there was an accident in Tennessee. Fortunately, there was no fatality, but as you can see, there were significant damages. The investigation report concluded that the main cause of boiler accident was improper maintenance and lack of operational procedures of boiler. The investigation recommended that all maintenance related to boiler should be performed by an experienced and qualified outside vendor knowledgeable in their operation and function. The first step of any startup begins with shutdown process. While planning for firing boilers after shutdown, it is important that utility manager should reassess and verify that every single step mentioned in boiler manufacturer's shutdown SOP is followed. If the process was not followed for some reason, or if there is a doubt, it should be highlighted and informed to the qualified startup technician so that hazard mitigation plan can be charted out. Now let's talk about feed water. There is no steam without water. It is important to verify proper operation of feed water system if it has been out of service along with boiler. Ensure that there is absolutely no blockage or debris all the way back to primary source of water. Feed water pumps operating and standby also need to be in service. This photo is from the same boiler accident that we discussed earlier. See the failed low water cutoff pump controller stuck in up position. This could have been the reason for the boiler continuing to fire even though boiler was experiencing a low water condition. The next critical component is the fuel and draft system. Irrespective of the fuel used, it is necessary to ensure fuel reaches the burner at desired temperature, pressure, and flow. In case of solid fuel boilers, the parameters can be much diverse, like moisture content, size, ash content, etc. The force and induced draft fans also need to be checked for normal operation. Check not only air dampers moving to their full range, but also check sieves at inlet of fan. Due to prolonged shutdown, sieves may have accumulated dust or water may have accumulated at the inlet. If there is an air heater installed, please ensure that controls and coils are in good condition. The auxiliary equipment like economizer, mountings like pressure gauge, vents and vacuum breakers and safety valves must be drained for any accumulated water or debris and visually inspected before firing the boiler. Since we want to just discuss common best practices, we'll not get into actual firing sequence and procedure as it is peculiar to a particular type and make of boiler. Please let us know if you want a webinar focusing on startup of a particular boiler. The next system is steam distribution system. In steam distribution system, the risk of failure is highest at system startup. If system is designed properly, condensate will drain itself off naturally. But since well-designed systems are hard to find, there will always be pockets or lengths of pipe which will accumulate water. This accumulated water in steam line is the single reason for almost all problems in steam distribution network. For starters, carbon dioxide in steam reacts with condensate to form carbonic acid. If you are wondering where carbon dioxide comes from, carbon dioxide originates from breakdown of carbonate alkalinity naturally present in makeup water. Due to purity of condensate, even minute amount of dissolved carbon dioxide is enough to lower condensate pH into corrosive range. Higher the alkalinity of makeup water, higher is the amount of carbon dioxide present in steam and higher is the corrosion. So it is very important to check that all the low elevation points are not accumulating any condensate. If while checking you encounter condensate sitting stagnant in a pipe elbow or sloping pipes, please make sure that the pipe is not corroded and safe for steam charging. If not sure, call in experts to help, but don't assume or overlook. The image that you see now is of an edible oil refinery. What you see here are three samples from left to right. First one is of feed water, the next is that of condensate from a leaking heat exchanger, and third is from condensate from a main steam header. As you can make out from color of condensate from header, carbonic acid has corroded steam header. If steam header had adequate and well-designed triplex with correctly sized inverted bucket steam traps, this could have been avoided. Carbonic acid also corrodes valves and flanges and any other threaded connections like pressure gauge or flanges. So whenever practically possible, check the operation of all valves and visually inspect threads of connectors and flanges wherever possible. The other consequence of condensate accumulation is water hammer. I'm sure you must have heard water hammer even though you may not have known what the cause of this water hammer was. During a tsunami, waves accelerated by high wind can cause severe damage even when forces are distributed across a very large area. Now think about this tsunami taking place in an enclosed steam pipe. Waves of accumulated condensate can surge through and block an entire cross section of pipe. When accelerated through piping by a shock, these waves can attain significant force. This is called water hammer. This is a photo of an 8-inch class 250 cast iron valve which was ruptured while being opened to 220 psi steam by a worker. The investigation found that the root cause of accident was water hammer caused by accumulated condensate. A closed gate valve under full steam pressure leaked steam into isolated section of line over 5 days and filled the line with condensate. There was a trap in the isolated line, but pressure was insufficient to discharge condensate from the trap. At the startup, full steam pressure was applied to water-locked line without noticing condensate accumulation. That completely ruptured the valve. So, to ensure a safe water hammer free startup, conduct a detailed steam trap survey to not only check the condition of steam traps but also adequacy in terms of type, size, and location. If there are locations with no traps where condensate accumulates, please install additional traps. Inverted bucket traps should be installed in water hammer prone area, as these traps by design are more resistant to water hammer. To ensure a safe water hammer free startup, manually check and drain water out of lines before steam is admitted. After it is confirmed that there is no water in system, that is the drains are open, then open the warm-up bypass. Any equipment larger than 6 inches needs a warm-up bypass. Allow system to warm up at the rate of maximum 100 °F per hour. The warm-up period for every plant will be different and will depend on many factors. A small low-pressure boiler in a compact plant, such as laundry for example, depending on size, could be brought up to operating pressure in a couple of hours, while a large industrial complex may take more than a day. As we discussed at the opening of this webinar, industries globally are facing a massive challenge of reinventing their product portfolio to match the changes in consumer behavior. Many stores have cancelled their regular shelf resets, meaning no new product will be introduced in this cycle. This has affected manufacturers who have made capital expenditures in anticipation of launching new and innovative products. This additional capacity or modifications now lay redundant. On the other hand, the hand sanitizer and wipes manufacturing industry is facing an exactly opposite situation. In normal startup, not much except general housekeeping is expected from steam utilization section. However, in this current startup, utility managers should be vigilant to changing dynamics and elasticity of installed utility system. If your industry expects a change in product or production mix, it is important to evaluate the adequacy of utility services required to run the change. Every steam system is unique, and a capacity bottleneck can ruin ambitious and otherwise wise business decisions. A thorough in-house or external steam system assessment in coordination with production and product design team is essential. It is also important to check the impact of change on system parameters on control equipments and process equipment. Going back to our earlier image, the oil contamination in condensate from heat exchanger is due to a phenomenon called stalling, in which subcooling of condensate in a heat exchanger causes carbonic acid induced corrosion. When the temperature control valve throttles steam, steam pressure differential across steam trap is not sufficient to drain condensate. This causes condensate to get trapped in a heat exchanger and release carbonic acid. Stalling can be easily eliminated by installing Armstrong's double duty pumping trap. Once the system adequacy is established for change or normal operation, careful attention must be given to overall process equipment. For example, the problem of startup at a refinery are much more complex. While sulfur-related fires are not common, they do occur occasionally during startup, shutdown, or during maintenance periods. A thorough inspection of sulfur pit is essential before startup. The next topic is condensate and flash steam. Condensate system, which includes steam traps, flash vessels, piping, and allied equipment, should be designed to handle peak steam condensation loads. However, many times it is observed that condensate system is inadequate for startup condition. Due to higher than normal loads, condensate and flash steam can get overpressurized and overflow. During prolonged shutdown, the float and level sensors can malfunction due to corrosion originating from accumulated condensate. The steam and condensate system that is sometimes designed decade back continues to run with 5 times more production. Design engineers always keep certain safety margins, but those limits are for safety and not for operation. So while planning for startup or when any changes to manufacturing process are made, a complete revalidation of condensate network is recommended. A steam trap survey before shutdown and focused on startup is important. The purpose of this survey is not just to identify leaking steam traps, but to verify correctness by type, capacity, and connection sizes. While conducting this trap survey, isolation valves and bypass valves for steam traps should also be checked. After verifying that existing system is good for the purpose, actual startup may commence. It is advisable to keep the drain valves open, but remember, the condensate coming out of drain will be at high temperature and flashing, so proper protective care, including earplugs, is recommended. Also, when draining out the condensate, minimize instances of draining in open. Special care should be taken to ensure that no hot condensate reaches to inflammable processing areas, especially in a refinery. Sometimes steam traps or bypass valves get clogged at startup. Do not violently hammer them. It can cause hot condensate to splash in the surroundings. One point not discussed so far is the thermal stress. Thermal stress can occur during startup due to rapid ramping up of system or inherent system deficiencies or just negligent workmanship. One incident that I remember was at a food plant where in-house design team had done the engineering and handed over isometrics to local fabrication contractor. The welding contractor welded all pipe supports to frame instead of keeping some of them floating for lateral expansion. Steam at 150 psi and 360 degree Fahrenheit was opened into pipe at full blast. This sudden temperature differential led to a lateral expansion which was restrained by the welded supports. 10 minutes or so in the startup and steam line took off from pipe rack like a rocket and landed some 30 meters away on an open ground. Fortunately, there was no fatality, but it led to months of delay in commissioning of a new production line. So no matter how small the job is, if you don't have expertise in-house, please consult experts for detailed engineering design. If there is one thing that we would really like to take home today, it just boils down to this. Do not use operational methods to permanently overcome design deficiencies in steam system. Just correct the steam system design. And this is where Armstrong can help you. Armstrong offers free introductory and advanced online courses, not just uh, focusing on utility systems like steam and hot water, but also has free courses on health and safety management. All these courses can be customized to meet your specific requirement. The link of course is mentioned here. Alternatively, you can simply search on the internet for Armstrong University and you'll land at the same page. Armstrong also has the most advanced learning center which offers classes on site. We can also set up remote training sessions to meet specific requirements. We have the live demonstration capabilities to show water hammer and trap operation through high resolution cameras. Armstrong's team of operational engineers is committed to deliver a swift and safe startup experience. It is the same team that for more than 20 years has operated and maintained utility systems across North America, allowing our customers to focus on their core business. We have maintained highest safety standards while ensuring close to 100% utility availability at every site that we operate. Armstrong, through its vast network of representatives, can help conduct steam trap surveys that are not just like any other survey, but tailor-made to help achieve a smooth and safe startup. Armstrong system engineers like myself and Navena and our counterparts globally are equipped to help you conduct a thorough system analysis to avoid pitfalls that we have discussed today. In context of COVID situation, we do understand and empathize with your apprehension in inviting an outside engineer for a startup. However, it is worth mentioning that even at the peak of this pandemic and even today, Armstrong's engineers at our O&M sites, as well as our representatives globally, continue to serve industries, hospitals, and essential service providers. We have put in finest practices and have embedded cutting edge technology to minimize physical presence at your site. We want to take this opportunity to let you know that we care and we are prepared for the job whenever you need a helping hand. Thank you very much.